This video was brought to you by GeneralPack.com, making power systems intuitive, open, and free to everyone, everywhere. Consider subscribing and supporting through patreon.com/generalpack. This is the mechanism for you to support us financially so we can continue making high-quality power system video tutorials. Our corporate sponsor for this topic is AllumiaX.com from Seattle, Washington. Contact them for industrial and commercial power system studies.
Reflecting a 3-line to ground fault on the high voltage side. In this video, we will see how we can actually take a 3-line to ground fault quantities, which is fault current and voltage quantities, which occur on the low voltage side of the transformer, but reflect them on the high voltage side. So first, let's have a recap of part 3A, in which we calculated fault current and voltage quantities for a 3-line to ground fault on the 13.8 kV bus. For a 3-line to ground fault type, we found that the positive sequence current was equal to negative J 6.67 per unit, and also that the negative and zero sequence currents were equal to 0. Now, to clarify, this was on the low voltage side of the transformer, and remember that there are no negative and zero sequence component for a 3-line to ground fault because it's a perfectly balanced fault type. This can be expressed as 6.67 per unit at the angle of negative 90 degrees in polar form. It's also important to note the subscript. The lower case indicates that the fault current on the low voltage side, the uppercase will represent fault current on the high voltage side. We will now proceed by reflecting these per unit current quantities on the high voltage side, and then we will multiply them with the appropriate base values to find the actual ampere current values. So, given that we have a DY1 or a DAB transformer connection, to determine the high voltage positive sequence component, we will shift the positive sequence component by plus 30 degrees, and that can be done by multiplying a low voltage fault current with a value of 1 angle plus 30 degrees. 6.67 per unit at the angle of negative 60 degrees is the positive sequence current on the high voltage side of the transformer. For zero sequence and negative sequence components, however, it will be non-existent because 3-line to ground fault, again, is a balanced symmetrical fault, and there are no negative and zero sequence components in symmetrical faults. Now, to convert these per unit values to ampere values in sequence components, we have to set up a base, but this time we are working on the high voltage side. So we divide the power value of 30 MVA by the high voltage side of the transformer, 115 kV, and we get 150.6 amps. And we just multiply out the per unit quantities with the base values to get the ampere quantities for the sequence components. We get 1004 amps at the angle of negative 60 degrees for positive sequence current. And then back to our familiar transformation equations, these quantities can be transformed to phase current quantities. But please note that we are removing the zero negative sequence currents from these transformation equations because they do not exist on the high voltage side, and we get the following. Plugging in the values of the A operator and the A square operator, as well as the sequence component values, we get the following. We find that the line A current is equal to 1004 amps at the angle of negative 60 degrees. Line B current is equal to 1004 amps at the angle of 180 degrees, and line C current is equal to 1004 amps at the angle of 60 degrees. Now this lines up very well with our current flow on the high voltage side. The fault current will flow on the high voltage side on line A, B, and C for a low voltage 3-line to ground fault involving all 3 lines. The reason why the fault current will flow on line A, B, and C of the high voltage side of the transformer is because the specific type is a DY1 transformer connection, as mentioned in part 4A of the series, and this can be visually seen in the diagram below. It also makes sense that the negative and zero sequence currents do not exist on the high voltage side. Even if we try to calculate the negative and zero sequence current using phase A, B, C current quantities on the high voltage side, we still get 0. For example, the equation for the zero sequence current is essentially 1/3 of the line A current plus line B current plus line C current as shown. And if we plug in these values, we simply get 0 for the zero sequence current component. And similarly, if we plug in the values for the negative sequence current equation, we also get 0 for the negative sequence current. Remember that the 3-line to ground fault is a perfectly balanced fault type, and it will be perfectly balanced on both the low voltage side of the transformer as well as the high voltage side of the transformer. Next, we will calculate the sequence voltage quantities, again reflected on the high voltage side of the transformer. To do that, we get back to our faulted sequence network diagram for a 3-line to ground fault and apply the KVL in the positive sequence network. We can calculate that the positive sequence voltage by considering the voltage of the positive sequence source 1 angle 0 degrees and the impedance of the source, which is J.05 per unit. Since J.05 is the only impedance on the high voltage side, the positive sequence voltage for a 3-line to ground fault is simply the source voltage minus the voltage drop across the positive sequence impedance on the high voltage side. For the positive sequence voltage, we need to consider the reflected positive sequence current on the high voltage side, which is 6.67 per unit at the angle of -60 degrees. So our equation becomes the following. And we get a value of 0.73 per unit at the angle of -13 degrees. Zero sequence voltage and negative sequence voltage will be non-existent because originally the zero sequence current and negative sequence current were also non-existent. We now have to set up a base to convert the per unit voltage to sequence voltage quantities. V base can therefore be taken as the following. Now multiplying the component of the base values, we get the voltage values in sequence component form. 48.51 kV at the angle of -13.2 degrees. Remember, these are still sequence voltage quantities. We have to use a 3 legacy transformation equations to transform the sequence component voltage quantities to actual line to ground voltage quantities. And also remember that we're removing the negative and zero sequence components from our transformation equations, and we plug in all of the values that we calculated earlier, and we simply get the following. We finally get the actual line A to ground voltage being 48.51 kV at the angle of -13.2 degrees. Line B to ground voltage is 48.51 kV at the angle of -133.2 degrees, and line C to ground voltage being 48.51 kV at the angle of 106.8 degrees. Now this is a very interesting result. Since the fault was a 3-line to ground fault, the fault currents in each phase were equal magnitude but displaced by 120 degrees. This directly correlates with the voltage magnitude as well. They are equal on each phase but also displaced by 120 degrees. And we see that there is a voltage depression on the high voltage side of the transformer, despite the fault being on the low voltage side. On the high voltage side of the transformer, our voltage quantities during normal operating conditions are 66 kV line to ground. But when there's a 3-phase fault on the low voltage side of the transformer, voltage quantities are depressed, and they're depressed to 48.51 kV. So they went from 66 kV to 48.51 kV. So there's quite a bit of a voltage depression even on the high voltage side. Now we hope this video was useful, enlightening for students and professionals. Please subscribe and donate to patreon.com/generalpack so we can continue making high quality power system video tutorials. Thank you.